Introduction to Aes Gcm mode. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics, focusing on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into Aes Gcm counter mode, commonly known as GCM. This is one of the most important authenticated encryption modes used in modern cryptography, and understanding it is essential for anyone working with secure communications. GCM combines encryption and authentication into a single, efficient operation. GCM is used everywhere in modern security systems. When you visit a website over HTTPS using TLS 1.2 or TLS 1.3, there's a very high chance your connection is using Aes Gcm. It's also used in IPsec VPNs, SSH, disk encryption, and countless other security protocols. Understanding GCM means understanding how most secure internet communication works today. In this presentation, we will explore every aspect of GCM in detail. We will understand what authenticated encryption means, how GCM combines CTR mode encryption with Galois field authentication, see complete examples with real data, and learn how to implement it correctly. By the end, you will have a thorough understanding of GCM without any ambiguity. What is authenticated encryption? Before we dive into GCM specifically, we need to understand what authenticated encryption means and why it's critical. Traditional encryption modes like CTR provide confidentiality, which means they prevent an attacker from reading your data. But confidentiality alone is not enough for most security applications. Consider this scenario. You encrypt a message using CTR mode and send it. An attacker intercepts the ciphertext. The attacker cannot read the message because it is encrypted. But the attacker can modify the ciphertext. With CTR mode, flipping a bit in the ciphertext causes the same bit to flip in the plaintext after decryption. The attacker can make targeted changes without knowing what the message says. For example, imagine you are sending an encrypted bank transfer. Pay Alice $100. The attacker cannot read this, but they know bank transfers have a predictable format. By flipping specific bits, they might change it to pay Alice $900 or pay Eve $100. This is called a malleability attack, and it is possible because there is no authentication. Authentication means verifying that the data hasn't been modified. With authentication, the receiver can detect if even a single bit of the ciphertext has been changed. If any modification is detected, the entire message is rejected. This prevents malleability attacks and ensures data integrity. Authenticated encryption combines both confidentiality and authentication. It encrypts the data to keep it secret, and simultaneously creates an authentication tag that proves the data has not been tampered with. GCM is an authenticated encryption mode, providing both security properties in one efficient package. GCM overview and components. GCM stands for Galois/counter mode. The name tells you exactly what it does. The counter mode portion means it uses CTR mode for encryption, which we covered in the previous presentation. The Galois portion refers to Galois field arithmetic, which is used for authentication. Let's break down the components. First, we have the encryption key, just like in CTR mode. This is your secret AES key, typically 128 or 256 bits. The same key is used for both encryption and authentication in GCM, which is more efficient than using separate keys. Second, we have the initialization vector, or IV in GCM. This is typically 96 bits, which is 12 bytes. The IV must be unique for each message encrypted with the same key, similar to the nonce in CTR mode. Many protocols just call it a nonce. The IV does not need to be secret, but it must never be reused with the same key. Third, we have the plaintext that we want to encrypt. This can be any length, and GCM handles it efficiently without requiring padding. Fourth, we have the additional authenticated data, abbreviated AAD. This is data that you want to authenticate but not encrypt. For example, in a network packet, you might want to encrypt the payload but authenticate the headers. The AAD is included in the authentication tag calculation but is not encrypted. This is optional. You can use GCM with empty AAD if you don't need this feature. The outputs of GCM are the ciphertext, which is the encrypted plaintext and has the same length as the plaintext, and the authentication tag, which is typically 128 bits or 16 bytes. The tag proves that both the ciphertext and the AAD haven't been modified. How GCM encryption works. Let's walk through the encryption process step by step. GCM encryption happens in two parallel streams. The encryption stream using CTR mode, and the authentication stream using Galois field multiplication. These two streams work simultaneously and are then combined. The encryption stream is pure CTR mode. You start with your IV, which in GCM is typically 96 bits. You append a 32-bit counter starting at 1 to make a 128-bit counter block. Notice we start at 1, not 0, because counter 0 is reserved for a special purpose in authentication. You encrypt this counter block with AES and your key to get a keystream block. You XOR the keystream with your plaintext to get ciphertext. You increment the counter and repeat for each block of plaintext. The authentication stream runs in parallel. GCM uses a technique called GMAC, which stands for Galois Message Authentication Code. Here's how it works. First, you encrypt a 0 block with AES using your key. This produces a value called H, which is your authentication key derived from your encryption key. This H value is used for all authentication operations with this key. Next, you process the additional authenticated data if there is any. You break the AAD into 128-bit blocks and multiply each block with H using Galois field multiplication, which is a special kind of multiplication used in cryptography. You accumulate these multiplications in what is called the authentication accumulator. Then you process the ciphertext in the same way. Each 128-bit block of ciphertext is multiplied with H and accumulated. After processing all the data, you create a final block containing the bit lengths of the AAD and ciphertext, multiply it with H, and add it to the accumulator. Finally, you encrypt counter block 0 using AES and your key. This produces a value that you XOR with your authentication accumulator. The result is your authentication tag. This tag is what proves that neither the AAD nor the ciphertext has been modified. GCM encryption flow diagram. The diagram on this slide shows the complete GCM encryption flow. At the top, we have the encryption path. The IV and counter go into AES encryption with the key, producing a keystream. The keystream is XOR'd with plaintext to produce ciphertext. This is exactly the CTR mode encryption we learned about previously. At the bottom, we have the authentication path. First, we generate the authentication key H by encrypting a block of zeros. Then we process the additional authenticated data through Galois field multiplication with H. Next, we process the ciphertext through the same multiplication. We add the lengths block and continue multiplying. Finally, we encrypt counter 0 and XOR it with the accumulated value to produce the authentication tag. These two paths work together. The encryption path produces the ciphertext that keeps your data secret. The authentication path produces the tag that proves the data hasn't been tampered with. Both the ciphertext and the tag are sent to the receiver, along with the IV, which is needed for decryption. Notice that the authentication operates on the ciphertext, not the plaintext. This is important. It means an attacker who modifies the ciphertext will invalidate the tag, even though they don't know the plaintext. This is called encrypt then MAC, which is considered the most secure approach to authenticated encryption. Understanding Galois field multiplication. You might be wondering what Galois field multiplication is and why GCM uses it. This is a special type of multiplication used in cryptography that has very useful properties for authentication. Let me explain it in accessible terms. A Galois field is a mathematical structure where you can add, subtract, multiply, and divide numbers following special rules. In GCM, we use a specific Galois field called GF2 to the power of 128. This means we work with 128-bit values, and our arithmetic follows special rules that make the math work out nicely for cryptographic purposes. The multiplication in this field is not the same as regular multiplication. It is a special operation that combines the bits in a specific way using XOR operations and bit shifting. It is important to understand that this multiplication has properties that make it perfect for authentication. First, the multiplication is fast to compute in hardware. Modern CPUs have special instructions that perform Galois field multiplication very efficiently. On Intel processors, there is an instruction called PCLMULQDQ that does this multiplication in just a few CPU cycles. This makes GCM extremely fast. Second, the multiplication allows us to accumulate authentication data incrementally. We can process one block, then another block, then another, and the order does not matter for security. We can even parallelize the authentication computation, which makes GCM even faster on multi-core processors. Third, the mathematics ensures that if even one bit of the input changes, the authentication tag will be completely different. An attacker can't predict how changing the ciphertext will affect the tag, which makes tampering detectable. The security proof of GCM relies on the properties of this Galois field multiplication. How GCM decryption works. Now, let's understand the decryption and verification process. When the receiver gets the ciphertext, the authentication tag, and the IV, they need to do two things. First, verify that the data is authentic, and then decrypt it. The order here is important. You should always verify before decrypting. First, the receiver recomputes the authentication tag using the same process as encryption. They use the received IV, the received ciphertext, and any AAD that's included. They generate the authentication key H by encrypting zeros. They process the AAD and ciphertext through Galois field multiplication. They create the lengths block and multiply it. They encrypt counter block 0 and XOR it with the accumulated value. This gives them a computed authentication tag. Next, the receiver compares the computed tag with the received tag. This comparison must be done in constant time to prevent timing attacks, but that's an implementation detail. If the tags match exactly, the authentication passes and the data is authentic. If even a single bit differs, authentication fails and the entire message must be rejected. You must not proceed with decryption if authentication fails. If authentication succeeds, the receiver proceeds to decrypt. Decryption uses the same CTR mode process as encryption. The receiver constructs counterblocks starting from counter 1, encrypts them with AES and the key, and XORs the resulting keystream with the ciphertext to recover the plaintext. Because CTR mode encryption and decryption are identical operations, this is exactly the same as encryption but with ciphertext as input and plaintext as output. The critical security principle is: verify first, decrypt second. Never output or use plaintext if authentication fails. An authentication failure means someone has tampered with the data, and you must reject the entire message. Some implementations make the mistake of decrypting first and checking authentication later, which can lead to security vulnerabilities. Simple example: encrypting a message. Let us walk through a concrete example to make GCM crystal clear. We will encrypt a short message HI, which is 2 bytes. We will keep the math simple for illustration, though real GCM uses proper 128-bit operations. First, let's discuss the setup. Our secret key is my key, beginning with 12, ending with 01, which is 16 bytes for AES 128. Our IV is IV, beginning with 12, ending with 12, which is 12 bytes. We have no additional authenticated data in this simple example. Our plaintext is HI, which is 2 bytes. H is 0x48, and I is 0x49 in hexadecimal. Step 1 is encryption. We construct counter block 1 by taking our IV and appending the counter value 1. Let's say this is IV beginning with 12 ending with 12 pipe 001. We encrypt this counter block with AES and our key. Let's say AES produces the keystream bytes beginning with 0x ending with AB and beginning with 0x ending with CD. We XOR the plaintext H, beginning with 0x ending with 48, with keystream, beginning with 0x ending with AB, to get ciphertext beginning with 0x ending with E3. We XOR the plaintext I, beginning with 0x ending with 49, with keystream, beginning with 0x ending with CD, to get ciphertext beginning with 0x ending with 84. Our ciphertext is beginning with 0x ending with E3 beginning with 0x ending with 84. Step 2 is authentication. We first generate the authentication key H by encrypting a block of zeros with AES and our key. Let's say this produces H, which is a 128-bit value, beginning with 12 and ending with DEF. Since we have no AAD, we skip that part. We process the ciphertext 0xe30x84 by padding it to 128 bits and multiplying with H in the Galois field. Let's say this produces an accumulated value. We create a lengths block. Our AAD length is 0 bits. Our ciphertext length is 16 bits, 2 bytes. We represent this as a 128-bit block and multiply it with H, adding to our accumulator. Finally, we encrypt counter block 0, IV with counter 0, with AES and our key. Let's say this produces 0xAABBCCDD. We XOR this with our accumulator to get the authentication tag. Let's say 0x7F8E9DAC. We output 3 things. The ciphertext, 0xE3, 0x84. The authentication tag, beginning with 0x7F, ending with AC. And the IV, beginning with 12, ending with 12. The receiver needs all 3 pieces to decrypt and verify. Simple example: decrypting and verifying. Now let's see how the receiver decrypts and verifies the message. The receiver has the ciphertext 0xE3, 0x84, the authentication tag 0x7F, 8E, 9D, AC, and the IV beginning with 12 ending with 12. The receiver also has the secret key my key beginning with 12 ending with 01. Let's walk through verification and decryption. Step 1 is authentication verification. The receiver recomputes the authentication tag using the same process. They encrypt a block of zeros to get H equals 0x beginning with 12 ending with EF. They skip AAD processing since there's none. They process the received ciphertext 0xe30x84 through Galois field multiplication with H. They create the lengths block, 0 bits AAD, 16 bits ciphertext, and multiply it with H. They accumulate all these values. The receiver then encrypts counter block 0 using the IV and key, getting the same value 0xAABBCCDD. They XOR this with their accumulator to produce a computed tag 0x7F8E9DAC. They compare this computed tag with the received tag 0x7F8E9DAC. The tags match exactly, so authentication passes. The message is authentic and hasn't been tampered with. Step 2 is decryption, which only happens after authentication passes. The receiver constructs counter block 1 from the IV, giving IV pipe 001. They encrypt this with AES and the key, producing the same keystream beginning with 0x ending with AB beginning with 0x ending with CD. They XOR the ciphertext beginning with 0x ending with E3 with keystream beginning with 0x ending with AB to get plaintext beginning with 0x ending with 48, which is the letter H. They XOR ciphertext beginning with 0x ending with 84 with keystream beginning with 0x ending with CD to get plaintext beginning with 0x ending with 49, which is the letter I. The receiver has successfully recovered the original message HI. If the authentication tag hadn't matched, the receiver would reject the entire message without attempting decryption. This is crucial for security. Any modification to the ciphertext, even a single bit flip, would cause the authentication to fail because the recomputed tag would be completely different. The role of additional authenticated data. Let us dive deeper into additional authenticated data, or AAD. This is a powerful feature of GCM that distinguishes it from simpler authenticated encryption schemes. AAD allows you to authenticate data without encrypting it, which is extremely useful in many real-world scenarios. Consider a network packet. The packet has headers that contain routing information, protocol details, and sequence numbers. The packet also has a payload that contains the actual application data. You want to keep the payload secret, so you encrypt it. But you can't encrypt the headers because routers need to read them to forward the packet. However, you want to authenticate the headers to prevent an attacker from modifying them. This is where AAD comes in. You pass the headers as AAD to GCM. GCM includes the AAD in the authentication tag calculation but does not encrypt it. The result is that the headers are sent in plaintext, but any modification to them will cause authentication to fail at the receiver. This protects the integrity of the headers while keeping them readable. Another example is database records. You might have a record with a record ID, timestamp, and user data. The record ID and timestamp might need to be searchable, so you cannot encrypt them. But you want to ensure they have not been tampered with. You encrypt the user data as plaintext and pass the record ID and timestamp as AAD. The authentication tag covers everything. In TLS, AAD is used to authenticate the record header. The header contains the TLS version, record type, and length. These cannot be encrypted because the TLS implementation needs to read them before decrypting the payload. But they are included as AAD so any tampering is detected. When processing AAD, GCM breaks it into 128-bit blocks, processes each block through Galois field multiplication with H, and accumulates the results. This happens before processing the ciphertext. The AAD is included in the lengths block at the end, so both the AAD length and ciphertext length are authenticated. If an attacker adds, removes, or modifies AAD, the authentication tag will not verify. Requirements and security. The initialization vector in GCM is critical for security, and there are specific requirements you must follow. Let's understand what makes a good IV and what happens if you get it wrong. The fundamental rule is that you must never reuse an IV with the same key. This is exactly like the nonce requirement in CTR mode, and it's absolutely critical. If you encrypt two different messages with the same key and the same IV, the security of GCM completely breaks. Not only does this break confidentiality like in CTR mode, but it also breaks authentication, which is even worse. Here's why IV reuse is catastrophic in GCM. When you reuse an IV, you generate the same keystream for both messages, which leaks information about the plain texts through XOR, just like in CTR mode. But you also reuse the same authentication key stream. An attacker can XOR the two authentication tags and derive information about the authentication key H with enough IV reuses. An attacker can completely recover H, and once they have H, they can forge authentication tags for arbitrary messages. This is a complete security failure. The standard IV size for GCM is 96 bits, which is 12 bytes. This size is recommended because it is efficient. With a 96-bit IV, The counter initialization is simple. You just append a 32-bit counter value to the IB. If you use a different IB size, GCM has to hash the IB first, which is slower. Most protocols standardize on 96-bit IBs. For generating IBs, you have two main approaches. The first approach is using a counter. You start at 1 and increment for each message. This requires maintaining state across sessions, but it guarantees uniqueness. The second approach is using random values from a cryptographically secure random number generator. With 96-bit random IBs, the probability of collision is extremely low if you are not encrypting a huge number of messages with the same key. Some protocols use deterministic IB generation, deriving the IB from message properties like sequence numbers. This works as long as the derivation ensures uniqueness. Whatever method you choose, the IB does not need to be secret, but it must be unique per message per key, and it must be sent with the ciphertext so the receiver can decrypt. Authentication tag length and security. The authentication tag in GCM is typically 128 bits, which is 16 bytes. However, GCM allows truncating the tag to shorter lengths, for example 96 bits or even 64 bits. Let's understand the security implications of tag length and when you might use different lengths. A 128-bit authentication tag provides very strong security. The probability that an attacker can forge a valid tag by guessing is 1 in 2 to the power of 128, which is an astronomically small number. For all practical purposes, an attacker cannot forge a tag. This is the recommended tag length for most applications. A 96-bit tag reduces the security margin but is still very strong. The forgery probability is 1 in 2 to the power of 96, which is still computationally infeasible to exploit in practice. Some protocols use 96-bit tags when bandwidth is at a premium, such as in constrained IoT devices or satellite communications where every byte counts. A 64-bit tag provides much weaker security. The forgery probability is 1 in 2 to the power of 64, which sounds large but is actually within the realm of possibility for a determined attacker with significant resources. A 64-bit tag should only be used when the application can tolerate the risk, such as in scenarios where a failed forgery attempt is quickly detected and the connection is terminated. It is important to understand that the tag length does not affect the encryption security, only the authentication security. Even with a shorter tag, the confidentiality of the encrypted data remains as strong as the AES key length. But a shorter tag means there is a higher chance an attacker could modify the ciphertext and get lucky with a forged tag that happens to verify. When choosing a tag length, you are making a trade-off between security and bandwidth. For most applications, especially Internet protocols, the 16-byte overhead of a 128-bit tag is negligible compared to the payload size, so there is no reason not to use the full 128 bits. Only use shorter tags if you have a specific bandwidth constraint and understand the security implications. GCM performance characteristics. One of the reasons GCM is so widely used is its excellent performance characteristics. Let us understand what makes GCM fast and how it compares to other approaches in terms of efficiency. First, GCM benefits from all the parallelization advantages of CTR mode. The encryption part of GCM is pure CTR mode, which means you can encrypt multiple blocks simultaneously. On a multi-core processor, you can have different cores encrypting different counter blocks at the same time. This makes encryption extremely fast. Second, the authentication can also be parallelized. While the final accumulation step is sequential, the individual Galois field multiplications for each block can be computed independently and then combined. This means you can process multiple blocks of ciphertext through authentication simultaneously, further improving performance. Third, modern CPUs have hardware support for GCM operations. Intel and AMD processors have the AES-NI instruction set which accelerates AES encryption, and the PCLMULQDQ instruction, which accelerates the Galois field multiplication used in GCM authentication. With these hardware instructions, GCM can achieve speeds of multiple gigabytes per second on a single core. Fourth, GCM combines encryption and authentication in a single pass over the data. You don't need to process the data once for encryption and again for authentication. The encryption and authentication happen in parallel as you process each block, which is more efficient than separate encrypt than MAC approaches. The performance of GCM is typically limited by memory bandwidth rather than CPU computation. If you are encrypting data that is already in CPU cache, GCM is extremely fast. If you are encrypting data from main memory or disk, the bottleneck is getting the data to the CPU, not the cryptographic operations themselves. Compared to other authenticated encryption modes, GCM is generally faster on hardware with appropriate instruction support. This is why it is the preferred choice for high-performance applications, like VPNs and web servers handling thousands of TLS connections. Complete encryption example with AAD. Let's work through a complete example that includes additional authenticated data to see how all the pieces fit together. We'll encrypt the message OK with AAD header 123. Setup. Our key is secret key beginning with 12, ending with 56, 16 bytes. Our IB is IB beginning with 98, ending with 10, 12 bytes. Our plaintext is OK, 2 bytes. 0x4F0x4B. Our AAD is header 123, 9 bytes. Let's walk through encryption step by step. Step 1. Generate authentication key H. We encrypt a block of all zeros using AES with our key. This produces H equal to beginning with 0xAA and ending with DD, simplified for illustration. Step 2. Process AAD next. We take header 123, which is 9 bytes, and pad it to 16 bytes to create a complete block. This block consists of header 123, followed by 70 bytes. We multiply this block with H in the Galois field. Let's say this produces beginning with 0x11 and ending with 44. This result then goes into our authentication accumulator. Step 3. Encrypt plaintext. We construct counter block 1 from IB beginning with 98 ending with 10 pipe 001. We encrypt this with AES and key, producing keystream A1B2. We XOR plaintext O, or 4F, with keystream A1 to get ciphertext EE. We XOR plaintext K, or 4B, with keystream B2 to get ciphertext F9. Our ciphertext is EEF9. Step 4. Authenticate ciphertext. We pad ciphertext 0xEE0xF9 to 16 bytes and multiply with H. This produces 0x beginning with 55 ending with 88. We XOR this with our accumulator. 0x beginning with 11 ending with 44x or 0x beginning with 55 ending with 88 equal operator 0x beginning with 44 ending with CC. Step 5. Process lengths. Our AAD is 72 bits, 9 bytes. Our ciphertext is 16 bits, 2 bytes. We create a lengths block. 72 in the first 64 bits, 16 in the last 64 bits. We multiply this with H to get beginning with 99 ending with AA. We XOR with accumulator. Beginning with 44 ending with CC XOR beginning with 99 ending with A equal operator beginning with DD ending with EE. Step 6. To generate the tag, we encrypt counter block 0. IB beginning with 98 and ending with 10 pipe 000, with AES and key, producing beginning with 0xFF and ending with EE. We XOR with the accumulator. Beginning with 0xDD and ending with EE XOR beginning with 0xFF and ending with EE equals beginning with 0x22 and ending with 33. This is our authentication tag, simplified to 16 bits for illustration. We send ciphertext 0xEE, 0xF9, tag 0x2233, IBIB, and AAD header 123 in plaintext. Complete decryption example with AAD. Now let's decrypt and verify the message we just encrypted. The receiver has ciphertext 0xEE, 0xF9, tag 0x2233, IB beginning with 98 ending with 10, AAD header 123, and key secret key beginning with 12 ending with 56. Step 1. Verify authentication. First, generate H by encrypting zeros. H equals beginning 0xAA and ending DD process AAD. Pad header 123 to 16 bytes and multiply with H, getting beginning 0x11 and ending 44 in the accumulator. Process ciphertext. Pad 0xEE, 0xF9, to 16 bytes. Multiply with H to get, beginning with 0x55 ending with 88. XOR with accumulator. Beginning with 0x11 ending with 44 XOR beginning with 0x55 ending with 88, equals beginning with 0x44 ending with CC. Process lengths. AAD is 72 bits, ciphertext is 16 bits. Create a lengths block, then multiply with H to get beginning with 99 ending with A, then XOR with the accumulator. Beginning with 44 ending with CC XOR beginning with 99 ending with AA equals beginning with DD ending with EE. Generate tag. Encrypt counter block 0. IB beginning with 98 ending with 10, 000, to get 0xFFEEXOR with accumulator. Beginning with 0xDD ending with EEXOR 0xFFEE equal operator 0x2233. This is the computed tag. Computed tag beginning with 0x22 ending with 33 matches received tag beginning with 0x22 ending with 33. Authentication succeeds. The message is authentic and has not been tampered with. Step 2. Decrypt. Construct counter block 1 from IB pipe 001. Encrypt with AES and key to get keystream 0xA10xB2. XOR ciphertext 0xEE with keystream 0xA1 to get plaintext 0x4F which is OXOR ciphertext 0xF9 with keystream 0xB2 to get plaintext 0x4B which is K recovered messages OK. The receiver has successfully verified the authenticity of both the AAD, header 123, and the encrypted payload, and recovered the original message. OK. If either the ciphertext, the AAD, or even the IB had been modified, the authentication would have failed, and the message would have been rejected. Implementation best practices. Implementing GCM correctly requires attention to several important details. Let's go through the best practices that ensure both security and correct operation. First and most critical, never reuse an IB with the same key. This cannot be emphasized enough. Implement a robust IB generation and tracking system. If using sequential IBs, store the last used IB persistently so it survives restarts. If using random IBs, use a cryptographically secure random number generator. Test your IB generation thoroughly to ensure uniqueness. Second, always verify authentication before decrypting. Your implementation should compute the authentication tag from the received data, then compare it with the received tag. Only proceed to decryption if they match exactly. The comparison must be constant time to prevent timing attacks. Never output plaintext or allow it to be used if authentication fails. Third, use appropriate tag lengths. For general-purpose applications, use the full 128-bit tag. Only consider shorter tags if you have specific bandwidth constraints and understand the security trade-off. Never use tags shorter than 64 bits, and even 64 bits should only be used in scenarios where you can tolerate the reduced security margin. Fourth, Handle the IV correctly in your protocol. The IV must be transmitted or stored with the ciphertext and tag. A common approach is to prepend the IV to the transmitted data. IV followed by ciphertext followed by tag. Make sure your decryption side reads the IV from the same location. The IV does not need to be encrypted but must not be tampered with, which is why it is often included in protocol-level integrity checks. Fifth, be careful with AAD handling. If your protocol uses AAD, make sure both encryption and decryption use exactly the same AAD. Any mismatch will cause authentication to fail. The AAD must be available to the decryption side, either by transmitting it or by reconstructing it from context. In network protocols, AAD often comes from packet headers that are already available. Sixth, use well-tested cryptographic libraries rather than implementing GCM yourself. Libraries like OpenSSL, Boring SSL, Libsodium, and Platform Crypto APIs provide thoroughly tested and optimized GCM implementations. They handle edge cases correctly and include protections against side channel attacks. Unless you are a cryptography expert, use these libraries. Real-world applications of GCM. GCM is used extensively in modern security systems. Let's explore the major applications where you'll find GCM protecting data and communications. The most prominent use is in TLS, the protocol that secures web browsing and most internet communications. TLS 1.2 introduced GCM cipher suites like TLS ECDHERSA with AES 128 GCM SHA 256. TLS 1.3 simplified the cipher suites, and all of them use AEAD modes, with GCM being the primary choice. When you visit an HTTPS website, there's a very high probability your connection is using Aes Gcm to encrypt the traffic. IPsec, the protocol for VPN connections and secure IP communications, extensively uses GCM. RFC 4106 defines how to use GCM in IPsec ESP, encapsulating security payload. Many corporate VPNs and site-to-site VPN connections use IPsec with GCM to protect the traffic. The AAD feature is particularly useful here for authenticating IP headers while keeping the payload encrypted. SSH, the Secure Shell Protocol, added support for GCM cipher modes. When you connect to a remote server via SSH, you might be using AES 128 GCM or AES 256 GCM to protect your terminal session. GCM's performance benefits make it ideal for interactive sessions where low latency is important. Disk encryption systems are increasingly using GCM while older disk encryption used CBC or XTS modes. Newer systems recognize the benefits of authenticated encryption. Some Linux disk encryption configurations support GCM, providing both confidentiality and tamper detection for stored data. Cloud storage services use GCM for client-side encryption. When you encrypt files before uploading them to cloud storage, many tools use GCM because it provides both encryption and integrity in a single operation. This ensures that not only is your data secret, but you can also detect if the cloud provider or an attacker modifies your stored files. Wireless security protocols use GCM. WPA3, the latest Wi-Fi security standard, uses GCM as one of its encryption options. This provides strong security for wireless networks with excellent performance on modern Wi-Fi chipsets that include hardware acceleration. Common mistakes and how to avoid them. Let's discuss common mistakes developers make when working with GCM and how to avoid them. Understanding these pitfalls will help you implement GCM correctly and securely. Mistake number 1 is IV reuse. We have mentioned this multiple times, but it is so critical that it bears repeating. IV reuse breaks both confidentiality and authentication. An attacker can recover the authentication key H with enough IV reuses. Always ensure your IV generation is robust and test it thoroughly. If you are incrementing IVs, make sure the counter is stored persistently. If you are using random IVs, use a crypto-grade RNG. Mistake number 2 is not verifying authentication before decrypting. Some implementations decrypt first and check the tag later, or worse, they output plaintext before verification completes. This can lead to serious vulnerabilities like padding Oracle attacks in authenticated encryption contexts. Always verify the tag first, and only decrypt and output plaintext if verification succeeds. Mistake number 3 is using the wrong AAD. If encryption and decryption don't use exactly the same AAD, authentication will fail. Make sure your protocol clearly specifies what the AAD is and how it's constructed. Common errors include AAD that depends on mutable state or AAD that's not available at decryption time. Mistake number 4 is incorrect lengths handling. The lengths block must contain the bit lengths of AAD and ciphertext, not byte lengths. If you accidentally use byte lengths, authentication will fail. Also, the order matters. AAD length comes first, then ciphertext length. Mistake number 5 is using weak keys. GCM is only as secure as the AES key. If you generate keys poorly, such as deriving them from passwords without proper key derivation functions, or using predictable seeds for random keys, you undermine the security. Always use cryptographically secure key generation. The 6th mistake is not handling edge cases. What happens if the plaintext is empty? What if AAD is empty? What if both are empty? A correct GCM implementation handles all these cases. Make sure your code is tested with various input sizes, including zero-linked inputs. Mistake number 7 is timing attacks in tag comparison. The tag comparison must be constant time to prevent attackers from learning information by measuring how long verification takes. Most crypto libraries provide constant time comparison functions. Use them instead of simple byte-by-byte comparison. GCM security guarantees. Let's discuss what security guarantees GCM provides and what it doesn't provide. Understanding the security properties helps you use GCM correctly and know when additional protections are needed. First, GCM provides confidentiality. Assuming unique IVs and a secret key, GCM encryption ensures that an attacker cannot learn anything about the plaintext from the ciphertext. The security of confidentiality depends on the AES key length. 128-bit keys provide strong security. 256-bit keys provide even stronger security for long-term protection. Second, GCM provides authenticity and integrity. The authentication tag ensures that any modification to the ciphertext or AAD will be detected. An attacker cannot create a valid tag for modified data without knowing the key. The probability of successful forgery is 2 to the negative tag length, which is negligible for 128-bit tags. Third, GCM is secure against chosen plaintext attacks. An attacker who can submit plain texts of their choice for encryption still cannot break GCM's confidentiality or create forgeries, as long as I-verses are unique. This is important for scenarios where attackers might influence the data being encrypted. However, GCM does not hide the length of the plaintext. The ciphertext has the same length as the plaintext, so an attacker can determine message sizes. In some scenarios, message length can leak information. If length hiding is required, you need to add padding at a higher protocol layer. GCM does not provide resistance against IV reuse. If you reuse an IV with the same key, security completely breaks. This is a fundamental limitation of the GCM design. Other modes like Aes Gcm SIV are designed to be more resistant to IV reuse, but they have other trade-offs. GCM does not inherently provide replay protection. An attacker can capture a valid GCM encrypted message and replay it later. The authentication tag will still verify because the message is genuinely from the sender. If replay protection is needed, you must add sequence numbers or timestamps at the protocol level and include them in the AAD. GCM assumes the key is secret. If an attacker learns the key, all security is lost. This seems obvious, but it means key management is critical. Keys must be generated securely, stored securely, transmitted securely, and rotated periodically. GCM's cryptographic strength doesn't help if key management is weak. Conclusion and summary. We've completed our comprehensive walkthrough of Aes Gcm/counter mode. Let's recap the key concepts we've covered. GCM is an authenticated encryption mode that combines CTR mode encryption with Galois field-based authentication, providing both confidentiality and integrity in a single efficient operation. The encryption side uses CTR mode with counter blocks starting at 1, while counter 0 is reserved for authentication. The plaintext is encrypted by XORing with a keystream generated from encrypted counter blocks. The authentication side processes the additional authenticated data and ciphertext through Galois field multiplication with an authentication key H, then combines the result with encrypted counter 0 to produce an authentication tag. The critical security requirement is never reusing an IV with the same key. IV reuse breaks both confidentiality and authentication, allowing attackers to recover the authentication key and forge arbitrary messages. IVs should be generated either sequentially with persistent state or randomly using cryptographically secure randomness. GCM's additional authenticated data feature allows authenticating data without encrypting it, which is extremely useful in protocols where some data must remain readable but still needs integrity protection. This is heavily used in network protocols to authenticate headers while encrypting payloads. Decryption must always verify authentication before outputting plaintext. This verify then decrypt approach prevents attacks and ensures that tampered data is rejected. The authentication tag provides strong integrity protection, with forgery probabilities that are computationally infeasible for full-length tags. GCM is widely deployed in modern security systems including TLS, IPsec, SSH, disk encryption, and wireless security. Its combination of strong security guarantees and excellent performance, especially on hardware with AES-NI and PCLMULQDQ support, makes it the preferred choice for authenticated encryption in high-performance applications. Thank you for your attendance. Please consider subscribing to the channel.